Example 2. Suppose that C of t represents dollars per day to heat your home, where t is in time measured in days, and t equals 0 corresponds to January 1st, 2018. We want to interpret what the integral from 0 to 90 of C of t dt represents. So notice here what our units are. C of t is in dollars per day. So dollars per day. Now, our time, or our independent variable, is also going to be in days here, just like the previous problem. So the days units are going to cancel. So whatever I get on this other side is going to be in dollars. And I know here we're talking about the cost, right, in dollars per day. So what this represents, we have to bring in the numbers that are here on the bounds. So this is going to be the total cost, or the total amount of money, you could say, or the total amount of dollars to heat your home during the first 90 days of 2018. So what are the key parts of this sentence? What are the things you want to make sure you have in your sentence? So we want to talk about this 90 days, or you could talk about from day 0 to day 90. You could say something like, roughly the first 3 months, but you need to talk about this time span because that's when it's happening. And then on the other side, we said that once we find this number, it's going to represent the amount of money. So I'm calling that total cost, but you could say something like, the total amount of dollars you spend, or money, the total amount of money you spend to heat your home. But what's important is that we're finding the units of the definite integral here, and we're also including the units of the independent variable. So that's our sentence, and let's try another. Example 3. Water is pumped out of a holding tank at a rate of 5 minus 4e to the negative 0.15 t liters per minute. So our rate is in liters per minute, where t is in minutes since the pump started. If the holding tank contains 1,000 liters of water when the pump is started, how much water does it hold 1 hour later? So there's a couple things about this problem that we need to be careful about. However, we have a general sense that the first thing we want to do is find out exactly how much water was pumped out, which we can do by finding the definite integral of our rate. So here we're going to find the definite integral of 5 minus 4e to the negative 0.15 t dt. So I want to remind you that my rate is in liters per minute, and time is in minutes. So whatever number I get is going to be in liters. It's telling me how much is being pumped out. Now, one of the places I need to be really careful is the question asks, how much water does it hold 1 hour later? But we said that time is in minutes. So whatever units your independent variable is in, that's what has to go on the integral bounds. So that means I need to think about how 1 hour is related to minutes. So I'm going to do this as 0 to 60, because again, this has to be in minutes since t was defined in minutes. So now I have this integral, and if I plug it all into my calculator, I'm going to get 273.34. And I said before that it's liters per minute times minutes, so this is going to be 273.34 liters. Now, we know that the holding tank initially contains 1,000 liters. In a previous problem, we added the amount from the definite integral to the initial value. However, we have to be careful here because we're talking about water being pumped out. So if that is the amount of water being pumped out of the tank, we actually have to subtract this number from 1,000. So normally, if our original function is decreasing, when we find our definite integral, we would get a negative number. But here, we have to use the words to understand what's happening in the whole scenario. So in this particular case, even though our function's decreasing, the way it's worded, we have to be careful and understand that we have to subtract it off, even though we got a positive outcome here, because the outcome is how much we pumped out. So we're going to do 1,000 minus 273.34. We're going to double check real quick, but these are both in liters, so we don't have to do any sort of conversion here. So 1,000 minus the 273.34 will give you 726.67 liters. So that's how much remains 1 hour later, because again, we've pumped out approximately 273 in liters. Let's look at another. Example 4. The function f of t gives a number of gallons of fuel used per minute, so gallons of fuel per minute, by a jet plane t minutes into a flight. The integral 0 to 30 of f of t dt represents, so again, we're interpreting what the integral means. So we need to consider the numbers on the bounds. So that's going to be the independent units. So that's time in minutes. So we're talking about what happens during the first 30 minutes of a flight. Now, my function has the units of gallons of fuel per minute times my independent variable of minutes. So when I take this integral, the result is going to be gallons of fuel. So just the gallons part. So if I was going to put together a sentence to talk about what this definite integral means, I would say something like the number of gallons of fuel used during the first 30 minutes, so that was our independent numbers over here, of a flight. So again, there's lots of sentences that are right, but we want to make sure we've included that we're looking at the first 30 minutes and that we're talking about the number of gallons of fuel that were used. So as long as those two pieces are in your sentence, then you're good to go. Let's look at another example. Example 5. The rates of growth of the population of two species of plants measured in new plants per year are shown in the graph below. Assume that the populations of the two species are equal at time equals 0. Part A. Which population is larger after 1 year and after 2 years? So let's start by looking at what's happening after 1 year. So after 1 year, we're looking at the area under the curve for these two species. So the area under the curve for species 2 is the area that's right here. And then the area under the curve for species 1 is going to be this whole area here. So we can see that there's more area under species 1 than under species 2, which means that we've grown more new plants for species 1 during that first year. So after 1 year, species 1 is bigger. However, if we look at what's going on after 2 years, we can see that what happens is that species 2 starts growing a lot more rapidly, and then species 1 doesn't grow quite as fast. So what we probably want to do is we want to approximate the area of each of these to get a sense of how big they are. So for species 1, it looks like we can draw in a little triangle here to approximate that area. So that area, I'm going to come up over here. 1/2 base times height. My base is 2 years long. And now my height, I'm going to say that's roughly 2250. So that's halfway between 1500 and 3000. It's right about there. So when we crunch that number, we're going to get approximately 2250. And then for species 2, I'm going to do something similar where I'm going to approximate this using a triangle. So here, the area under this curve, I'm going to do 1/2 base. Now my height is quite a bit higher than it was for our first species. So I'm going to approximate that to be approximately 3,900. It's a little bit above the halfway point, which is 3,750. So partially between 3,750 and 4,500. You could call that 4,000. But what really matters here is any estimate you get between 3,750 and 4,500 is going to give you a result that's larger than what we got for species 1. So after 2 years, species 2 is going to be larger because, again, there's more area under the curve of species 2 at time equals 2 than under species 1. So part B wants to know, how much does the population of species 1 increase during the first 2 years? Well, we actually found that when we were comparing. So during that first 2 years, it increased by 2250 because that was our approximation of the area under the species 1 curve. So again, if you want to compare how big two species are or two populations, you're looking at the area under the rate curve and you're trying to determine which area is larger. Sometimes it's really obvious and you don't have to do any calculations, but sometimes it's better to actually get a rough estimate of what it is to make that kind of comparison. So let's look at an application of this that's really important in the medical field.